Department of Mechanical Engineering, Jyoti Engineering College, sponsored by ATAL Academy, New Delhi. And we are going to start with the 14th session. We are extremely glad to have with us Dr. N. Sendhil Kumar to lead the session. Dr. N. Sendhil Kumar completed his B.Tech Mechanical Engineering and M.Tech Energy Engineering from Pondicherry University and PhD in Mechanical Engineering from Indian Institute of Technology, Madras. He also did his postdoctoral research at Heriot-Watt University, Scotland, United Kingdom. He has more than 12 years of working experience, which include both teaching, research, and industry. Currently, he is working as head of the department in mechanical engineering, National Institute of Technology, Puducherry. During his service, he also served as member of Board of Governors, NIT Puducherry, Research and Consultancy Coordinator, Chairperson for Scrutiny Committee for PhD Admission and Staff Requirement. Dr. Sendhil Kumar has executed many funded
Yes.
and consultancy projects funded by various agencies including Department of Science and Technology, National Institute of Ocean Technology, and many more. He has published several research articles in peer-reviewed international journals, national and international conferences. His area of interest include solar thermal collectors, concentrating photovoltaic, integration of high temperature solar thermal and CPV fuel cells, heat transfer, fluid flow, and jet ejectors. With utmost happiness, on behalf of the Department of Mechanical Engineering, Jyoti Engineering College, I extend our heartiest welcome to you, sir.
Yes, sir. Thank you. So, sir, shall we start?
Yes, Professor.
Yes, sir. So, thank you for the introduction. Actually, today's section is how to overcome the problem of medium and high temperature concentrating solar power technology. This is the thing we are going to see actually. I hope you know in the previous sections what is concentrating solar power technologies, shortly called as CSP. I hope you know that, and then most of the basics of solar energy also have been covered in the previous FDP. So anyhow, a few glimpses I will give about the introduction about the solar energy, and then what are the necessary thing is required for designing the concentrating solar power. In that aspect only I will see, and then we are going to see about the different types of concentrating solar power technology, and what are the problems mainly involved in the concentrating solar that is solar power technology, and how to overcome this. And we have done some case studies also. Practically, we have developed the system that also I will share actually at the end of the presentation. And finally, what are the research work we are doing at NIT Puducherry, that also I will like to share here with respect to concentrating solar power technology only. So I hope the introduction has been given. I am working as a assistant professor and head in the Department of Mechanical Engineering, Associate Dean Faculty Welfare. If you have any doubt after the presentation, or if you want to see my research papers, you can send email to this email ID given here. Now with that, I will other things. So here the medium and high temperature we are going to see mainly, and then what are the problems associated with that, that also we are going to see. This is the thing content I am presented here. So before seeing the concerning solar power technology, few slides I want to give about the introduction to solar energy. I will quickly rush up this section so that we will mainly concentrate on the concerning solar power technology. Okay, I hope you have studied that from the sun we are getting the two types of radiation. One is direct beam radiation, other one is diffuse radiation. The summation of direct beam radiation and diffuse radiation is called as a global, that is global radiation actually, global solar radiation. This is the thing. And for considering solar power technology, mainly the system will reflect the direct beam radiation only. So we are mainly particular about the direct beam radiation, for especially for concentrating solar power technology. And we should know how much solar radiation is coming to the earth. All those information are there. You can see that the solar constant. I hope you read that solar constant. That is so 1367 watt per meter square. How much solar radiation is available
Professor?
above the earth atmosphere? Yes. Hello.
Professor, the PPT is not visible. Can you share it one more time? Can you end the PPT and can you present it one more time?
Is it visible, sir? Is it visible?
Yes, Professor. Now it is visible. Yeah. Thank you.
So the direct beam radiation is very, very important here, because when you say about concentrating solar power technology, it will reflect only the direct radiation, whatever we are getting from the sun, and then it will not reflect the diffuse beam radiation. Diverse number actually. It is a working principle of parabola only that we will see in the next slide. That's why this what are the radiations coming from the sun, that is very important. So global solar radiation, that is for flat plate collector, all those only it will be useful. But here, considering solar power technology means that is direct beam radiation is required. That is the thing. So total amount of radiations coming to the earth, it is 1367, out of which some of the radiations will be lost actually. So almost 80% of this only reaching to the earth. After 1000, we can say it is 1000 watt per meter square, 1 kilowatt. That is the thing. And the surface temperature of the sun is 5500 degrees centigrade. So it is 5773 Kelvin. This is the outer surface temperature of the sun. That is also very important. How much sun is we are getting? Because one sun means a lot of terminology they used to say actually one sun means that is 1000 watt per meter square. One. So 100 suns means 100 watt per meter square. This is the terminology they used to in the designing of constant solar power systems. Okay, next, you know the spectrum of solar radiation. That is, the solar spectrum is 0.1 to 3 micrometer, whereas the thermal radiation spectrum is 0.1 to 100 micrometer. So the solar spectrum is very, 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 very small when compared to thermal radiation. You can see that 0.3 micrometer only. That is the thing. So this is the spectrum of solar radiation. And then from the sun, if you plot the spectral irradiation with respect to the wavelength, the curve will look like this only actually. So with that, you can easily predict the surface temperature of the sun, whatever we said actually. That is 5500 degrees centigrade. If you plot that curve, what is the maximum wavelength for the particular point, you can easily evaluate the surface temperature of the sun. This is lambda max T equal to 2898 micrometer Kelvin by using the Wien displacement law. And those who are in the heat transfer side, they know that based on that we can predict the surface temperature of the sun. These are all very basics I am telling. Anyhow, this Earth-Sun distance and what is the diameter of the sun, what is the diameter of this given here. You can see that diameter of the Earth is 1.27 10 to the power of 1 meter, and the sun is 10 to the power of 9 meter, and the distance between is 10 to the power of 11 meter actually. So here the thing is, the Earth and the sun is not exactly in line actually. You can see that it is not exactly in line. So conical rays are coming from the sun. Actually, if you see that cone angle will be there actually, that is very, very important in the designing of concentrating solar power systems. From the sun, we are getting the conical rays. From the sun only we are getting to the earth actually. That is, earth and the sun is not exactly in line. It is slightly offset actually. So because of only we are getting almost parallel rays from the sun, we are almost saying most of the books. So that's conical angle is a 0.53 degree angle that we will see in the designing of the CSP. This information is very important for designing the constant solar power. And of course, know about the different seasons also. Different seasons, the declination, designing of concentrating solar power system or any solar thermal systems, how much amount of global radiation for today's date, say for example today is September 25th, so what is the radiation level, all those things also you should know. So for that you should know the seasons. So 4 seasons are there. One is summer solstice and winter solstice and equinox. The equinox means the declination, that is sun is exactly at the straight line path during some September and March. September 20, you can assume 21st or 22nd. You can say that constantly you can assume the 21st. So September 21st and March 21st, the sun is at exactly at the inline. That is inline means it is exactly at the straight line path. Whereas in the summer solstice and winter solstice, summer solstice means June 21st and the winter solstice means December 21st. So in the summer solstice plus 23.5 maximum declination, and the winter solstice minus 23.5 declination. This is the thing. So that is if you track the sun means, because for tracking this information is important. So how to install the tracking system, how to capture the sun orientations, all those things. So the winter solstice means December 21st, it is minus 23.5. It is extremely minus 23 extreme end, and summer solstice means plus 23.5. This is for us. And of course, if you want to predict the how much amount of solar radiation is coming to the earth for the particular day, you can easily predict by using this analytical expression. It is also there actually. That is how much amount of the solar constant is available in the particular. Where I mentioned 1367, that is the mean global, that is mean solar radiation. It's available above the Earth atmosphere. That is the thing. And some angles are also very important in designing the constant power systems. You should know about what is zenith angle, what is solar altitude angle, and azimuth angle. You can see the picture actually here. When sunrise is there actually, so angle between the vertical line and the sunrise angle, that is known as the zenith angle. Zenith angle means it is very important. It is that if suppose if standing here means above the overhead of your head, that is the vertical line. So if angle between the sunrise and the vertical line, the vertical angle is known as zenith. And solar altitude, that is angle between the sunrise and the its horizontal image on the horizontal that is projected sunrays on the horizontal plane. Angle between sunrays and the projected image on the horizontal plane. Projected sunrays image, that is alpha. Here is solar altitude, and other one more angle is solar azimuth angle. That is, since we are in the northern hemisphere, always we are facing our intersystem the south actually. It's angle between the projected image and the horizontal plane to the due south. That is known as the solar azimuth angle. So these three angles are the very basic angle. You should know this while designing the systems. Of course, we can declination. I already told you that September and March is the equinox 0 degree, and then June and December 21st is the summers and winter solstice. So if you want to predict the angle, the declination in between, you can easily predict by using this analytical expression for entry. Suppose today is 25th of September. So you can assume this is at 0 degree. It is slightly, it is, we can say that the declination will be 0 today almost. You can stay like this. Then this is the analytical expression, you can find that. And what are the losses? Losses means in the atmosphere, a lot of water particles and dust particles are present. So that whatever radiation is coming to the earth, it has to pass through the atmosphere actually. So in the due course, what will happen? Radiation will be lost. The particles present in the atmosphere will be observed or scattered. Scattered means other path actually. It will not come to the earth actually. And then some radiation directly coming from the sun to the earth. That is called as a direct beam radiation. And some portion of the radiation will project somewhere and then it will come to the earth. That is called as diffuse radiation actually. Anyhow, you can see that almost 80 to 80% only beam radiation and 20% will be the diffuse radiation. You can say, you can assume like that. That is the thing. So this will give the overall picture about how much amount of solar radiation is coming to the earth. So what type of equipment we can use? Already you might have seen. I quickly will just say pyranometer. That is this for measuring the global radiation. We use the pyranometer. Measure the global radiation component. If you use circular ring, you can measure the diffuse component. That is the thing. Of course, you can measure once you know the global radiation and circular ring by using diffuse component, you can find the beam radiation also. If you want to separately find the beam radiation, how much amount, that is, you have to use the pyrheliometer. Pyrheliometer will measure how much amount of direct beam radiation is coming to the earth actually. That is the thing. So with the acceptance angle of 5 degree, how much cone angle is coming, that only it will be taken. Applications, of course, you know that all the applications, solar water heating system, and then solar heating of the buildings. These are the applications of solar energy. You can vary that, and solar distillation, that is how to convert the brackish water or sea water into drinking water, all those things. And, drying, how to remove the moisture content present in the food substance. We are also working in that, and solar furnaces and solar cooking. These are the applications of the solar energy. Of course, I know to describe further because you might have read in the previous section. It might have covered actually. Elaborately, we'll see the constant solar power system. These are the solar pumping. So whatever the power required for the pump, so that will be for the power will be given by the PV panel actually, or electrical power generation also will be there. We can separately install the PV that is panels to generate the power. That is also that. These are applications of the solar thermal as PV. Now the 4 important things I am going to give the application of solar energy. With that only our session going to start actually. So these are one of the thermal power production, that is converting solar energy to thermal energy. That is, so here different technologies are available. One is solar parabolic trough, solar dish, and then solar central receiver, and then compact linear funnel reflectors. These are 4 covered. Anyway, this greenhouse effect is also another application. Conversion, you can see this is the solar parabolic trough actually. So it's a line focus. You can see it here, the picture. Elaborately, we'll see that these are the things we are going to see that parabolic trough, and then linear funnel reflectors. So here, when compared, this is also when this is a line 2D parabola. Here it is line focus actually. Line focus. Here also it is look like a parabola only. You can see that glass reflectors are there, no? That is arranged as a parabola only. But the only thing is, it is not a continuous mirror, it's elongated mirror. You can see that. It doesn't look like a two parabola. But the only thing that is, you can track the mirrors individually. So the more effort is not required for tracking system. Whereas in the previous slide, you can see the trough, it is an individual system actually. If you want to track, the entire system should be tracked.
Excuse me, Professor.
This is all coming under medium temperature.
Professor?
Tell me, sir.
Actually, the bandwidth is very slow. I think
Hello.
there is some problem with the network. Hello? Professor, there is some problem with the network. Your
Yes.
voice is breaking. So if you mute the video, that will be fine. We will get some speed.
Okay, sir. Okay.
Thank you. Thank you.
Yeah, now it is visible, sir. Okay. So now is it clear? Presentation.
Yes, sir. Yes. Presentation is clear.
Voice is also clear, no? Yes.
Now it is clear.
Thank you. Yes.
Thank you, sir. Thank you.
So this is also look like a parabola. You can see here. Yes. And the only yes, sir. Yes, sir. Thank you, sir. Thank you. The only thing is here we are not using a continuous parabola structure. Actually, we are using a discontinuous reflectors. Actually, the purpose of is you can individual mirror can be tracked. Actually, tracking means anyhow we are seeing in the elaborately how it is focusing all those things. This is the one type of concentrating solar power technology only. This is the linear funnel, that is linear funnel collectors actually. Third one is that is central receiver solar power tower. This is possible only in the desert region. Huge area is required. Here heliostats are used. Here there is no parabola. If you see the birds, if you see, it will have to look like a parabola only. You can see that it's also look like a parabola, but the focusing point will be at the top of the chimney actually. At the center point, one chimney is there. So above the chimney, one river is placed actually. That is the thing. So all the reflectors is called as the heliostats here. All the heliostats will be focusing on the receiver. Depends on the sun orientation. Suppose sun in the east means only that particular portion of the heliostats will reflect the solar radiation. So not all the things we use actually. Okay. Now after that, last type is the solar parabolic dish. This is similar to the central receiver. This is also like a point focus actually, 3D structure actually. 3D structure. Now here it mainly concerns that's 3D structure. Here only the entire system should be tracked actually, not individual mirrors also. So entire whole system should be tracked to focus the sun orientations. That is the thing. This is the fourth type. Now elaborately we are going to see what are the problems present in that parabolic dish, parabolic trough, central receiver, and then compact linear funnel reflectors, and how to overcome this. All those things only I am going to elaborately discuss. Yeah, you can see it here, concentrating solar power technology. So in that, 4 systems are there. Now the medium, we are mainly concerning with medium and high temperature. Anyhow, of course, solar flap reflectors and other systems are coming into the low temperature that we are not concentrating actually. Now here we are mainly dealing with concentrating solar power technology with that medium and high temperature. So here medium temperature means the temperature will be less than 400 degrees centigrade, and high temperature means greater than 400 degrees centigrade. So according to that, the central tower and solar parabolic dish coming under the high temperature, it will produce the more than 400 degree. It is a 3D structure actually. 3D, here it is a point focus. You can see that point focus. So it's a minimum 2 axis, 2 tracking is required minimum actually. Whereas here, and the medium temperature, the temperature is less than 400 degree, and this parabolic trough and then funnel reflectors are coming under the medium temperature application. Especially this, you can see that it's a 2D structure. A 2D means it's a line focus actually. You can see that the focal plane is in the line, focal point. It's not a point, it's a line, focal line actually. So these are the classifications of medium temperature and high temperature solar concentrating solar power technology. So first let us take one by one. Before that, we will have the comparison about all the systems. you can see that parabolic trough requires minimum of one axis tracking, and the compact linear funnel reflector CLFR, it requires also only one axis. If you use two axis, that is also good actually, but minimum one axis is required. But solar power tower and the solar parabolic dish, minimum two axis is required, because to locate a point in a space, minimum x and y coordinates, similarly that is two axis is required for that here. And then constant ratio among all the technology, parabolic dish is having highest value. That is, you can see that 8,000 is the so far the reported constant ratio 8,000. You can see the 8,000 means it is suns, 8,000 suns. I can say that one sun means 1,000 watt per meter square. 8,000 suns, you can imagine such a huge amount of heat flux is available at the focal point, so that we can concentrate to one particular small point. This is the thing. And the compact linear funnel reflector, it is 80 only, maximum 80, because it is a 2D. I already told you, it's a line focus. It is heat is scattered actually. That's why this 80 is the constant ratio or suns. And operating temperature also, of course, 400 degree parabolic trough and the compact linear reflectors. And here we can go up to 1200 degree, and here up to 800 degree we can go. That's why it's coming under the high temperature application. And the efficiency, you can see that thermal to solar efficiency, it is 80% is in the solar parabolic dish, because area is very small. So converting solar to thermal efficiency is very high actually. There is heat loss is less actually. Whereas here compact linear and the parabolic trough, the efficiency maximum solar to thermal conversion is 56% actually, and the tower is 73%. These are the comparative study. You can see that actually. Now elaborately we'll go one by one. The solar parabolic dish. First, let us take. We are working in the solar parabolic dish almost past 12 years actually. I have been developed one solar dish during PhD time also. So I have been experienced in the solar parabolic dish almost 12. After that also I have developed two dish. So if you have any clarifications or anything, if you are working in the solar dish, if you have any doubt, you can please feel free to contact me how to address all the problems. So we will see the solar parabolic dish as the first constant technology, because that is the highest concentration ratio I mentioned actually. That's why I'm taking this. This is not the new technology. This is the old one. How Germans used the parabolic reflectors to burn the mirrors, to burn the woods actually. How Archimedes used the mirrors to burn enemy ships. You might have heard the story. He used the parabolic reflectors only. This is the thing. So this is not the new one. This is the old one. Now we are using the technology, and we want to improve the technology only. Even in the Olympic also, they use the solar parabolic reflectors to ignite. They thought that it's fire is given by the god actually. That is a Greek mythology. Still, the parabolic reflectors only they are using. You see the polished reflectors. You can see that. Now let us come to the technical side. Here I had drawn the parallel rays. You can see that solar parabolic dish I had drawn, and then the parallel rays I had drawn only, not conical rays. Here main three components. One is a concentrator, other one is receiver, and third one is tracking system. These are the three things required for the concentrating solar power technology. The concentrator means the function of the concentrator is to just reflect the solar radiation, that is direct beam radiation, onto the receiver point. It is now concentrating. So if you measure how much flux is available on the solar, on the parabolic structure, means you will get only 1,000 watts square. The same flux, if you measure at the receiver side, it will be multiplied actually. That is, now it is focusing now. So it is concentrating small area. It is flux is increased actually. So energy is not increased, flux is only increased. So here 1,000 watt per meter square. Let us imagine there it is depends on the concentration ratio. It will be multiplied. So let us imagine it is a 200 suns, means 1,000 into 200 watt per meter square will be available at the focal point. Here it is a point actually, I can say. Point means it's a small ideal point. It's ideal case it's a point, but in actual case it's not a point. It is scattered actually. So you have to design accordingly. So the three components are very, very important. One is that is parabola, that is concentrator, and second one is receiver, and the third one is tracking system. These are the three things. So let us see the things, other things. What is the ideal concentration ratio we can produce in the solar parabolic dish? Means you can produce 46,747 ideal concentration ratio. This is the maximum concentration ratio we can achieve in the solar parabolic dish. How this value has come means you can see that the diagram, sun and the earth. Earth is very small when compared to the sun. You can see that the conical rays is coming from the sun. That angle is 0.3 degree actually. The sun diameter know the distance between the thing. 3 is the conical angle we are getting actually. But the problem is, if you are designing the system properly, the same 3 degree will be made. So in this case, you will get the ideal as a point. But the problem is, we cannot design the system properly, because if any error, small errors is present in the contour of the parabola, that is, if the parabola not look like a parabola, some cylindrical shapes, this angle will increase actually. Instead of 0.3, you will get 1, 2, 3, or 4, depend on that. So what happens? Incident angle will not be equal to the reflected angle, so you will get a scattered image actually. That is the thing. So here the maximum is on the scattered image to design the receiver. That is the thing. So the receiver will be placed at the focal point, concentrator is the base actually, and then tracking system to track the sun, because sun is moving from east to west every day. So we have to track the sun continuously. Why we are track? Because we are reflecting only the direct beam radiation onto the receiver. Okay, the system will reflect only the direct beam radiation. That's why we have to track the sun from east to west actually. That's why it's called as a concentrating solar power technology. Actually. So this is the ideal case. 46,000 times we can 46,000 times constant ratio we can produce. That is the ideal case. And then yeah, another one is now we come to the parameters. We have seen the component, 3 components. One is concentrator, second one is receiver, third one is tracking system. And then terminology, what are the terminology will be used here means focal length. You of course know the focal length, the distance between the base of the, from the base of the concentrator to the focal point. That is known as the focal length actually. And then other one is rim angle. Rim angle is very important here. The rim angle depends on the rim angle only, what type of solar dish you are using, that can be predicted. So the psi is the rim angle. The rim angle means the extreme angle between the extreme rays to the optical axis. That is called as a rim angle. Here you can see that rim angle. This is the rim angle actually. And then focal length, you know, of course, diameter, you know, diameter of the dish means this is the diameter actually. That is the thing. So these are the terminologies involved in the solar parabol dish. Now let us see that the rim angle, effect of rim angle, you can see that the top one is the also a parabola and the bottom one is also a parabola. You see the rim angle effect. So this will be coming here, the focal point will be inside. For this dish, the focal point will be outside. You can see in very clear picture, you can see that deep dish and shallow dish. The deep dish means the rim angle is greater than or equal to 90 degree. Either it will be outside the solar parabolic structure, or otherwise at the surface, at the aperture, the aperture side of the receiver. Receiver used to play. Receiver means that is our cooking spot, because deep dish mainly used for cooking purpose actually. That is thing. And the shallow dish here, the rim angle is less than 90 degree and the longer focal length. So the focal point is lying outside the parabola. You can see that outside the parabola. So you can see that this is called as a shallow dish meant for power application. That is the thing. So rim angle is play a major role. Optimum rim angle is 60 to 70 degree is the optimum rim angle for the power generation type. Normally power generation means receiver also play a major role. There is cavity type receiver will be used. You can see it here. So first let us see the constant technologies are available and how it will be made. So you know that it reflects the function of the constant is to reflect the direct beam radiation onto the receiver. So now due to this, continuously we have to track the sun. That also you know that. So these are the technologies available. Thin glass with silvered on back, single paraboloid facet, multi-paraboloid facet, fixed membrane, all those things are there. You can see that one by one. This is a glass facet. Glass facet means at the back side coating will be there. So that will be used as a glass facet. So that it has some reflectivity value. And then it will focus onto the, you can place, anyhow you have to make the structure parabola, and over the parabola or on the parabola you have to align the mirrors actually. Your mirrors, you can optimize the shape of the mirrors, and you can use the rectangular. Now it is called as faces, and you can see the n number of faces are there. And then you can see that slope error is one of the main important thing. Slope error means how much amount of that slope error, because how much amount of deviation is there. All the things in the slope error, how much amount of manufacturing error is called as a slope error. Suppose here you can see cost also will increase. If you want accurate parabola, cost also will increase. If you don't have cost means you can produce only the low cost parabola. So that the parabola shape will not be in that is look like a parabola. You can see that that is lead to a slope error. That's called as a slope error. You can see that slope error for this case is 0.5 milliradian. And the constant ratio, you can see that it is 2800. 2800, you can imagine 1000 watt per meter square is coming. Multiplied with the 2800, it will be available at the heat flux at the receiver actually. So F by D ratio is 0.6. rim angle is 40 degree. Say that. Now, second, this is also glass facet concentrator, but the dish actually. This is the different concentrator showing actually. Here the concentrator is 2793 actually. Similarly, we have a lot of technology, sometimes full surface parabola, and then these are the full surface, and then structured membrane means in membrane will be there. In order to acquire the shape of the parabola perfectly, they will just withdraw, they will just pull the membrane to the back side by using vacuum, and then you will acquire the shape of the contour. Suppose anyhow, if you have to produce the structure parabola, then only this membrane also will acquire the same shape. Here also, this is the structured membrane, single facet structure, single one membrane will be there. This is also a single facet, and this is the multi-facet structured membranes. Multiple membranes are there, and but our focal point is one actually. That is it. These are the different technology, concentrated technologies available. So simple technology means we can use the facet mirrors. Facet, that is whatever the plain glass mirror we are using for our face mirror, that can also be used, or acrylic mirror can be used. What type of reflectors we are using, that is also play a major role here. So this is the multi-facet. And then what are the problems involved in that concentrator means, only thing is accurate parabola structure we have to produce. That is the main thing. But how to minimize we can, if you want to minimize, anyhow, the shape of the parabola we have to compromise, that is the thing. So for that, what we have to do, we have to, okay, let it be the low cost, low profile parabola, but I will take design details in the receiver. That is also their options are there. So these are the problems to overcome that. Otherwise, if you want to perfect parabola means you have to small facet size should be, you have to reduce. That is another thing you can do that. Facet size means if you are using bigger facet size, it will be more. So that you can use small facet size, so that the error will be very less also. And then instead of rectangular facets of centimeter by 5 centimeter, if you use, instead of that, if you use the 2 centimeter or 1 centimeter as a square rectangle, then it will be minimized actually. Instead of 5 centimeter by 5 centimeter, if you use 2 centimeter to the facet size you are using, so that the slope error will be minimized actually, so that it will occur the shape of the parabola. If you see that, but only thing is the structure should be a perfect parabola. Whatever I'm telling, that is only for reflectors I'm telling. If even your base structure is very good, but if you're not aligning the phases properly, means again it leads to slope error. Then you get instead of point, you will get a scattered area. So for that, you have to make the structure very parabola, structure in that is parabola contour in a good shape, as well as the aligning, placing the facets also. These are the problems in the concentrator, and how to overcome. We have to align. We can take the shortest, that small distance, small facet size. You can take as small as possible. What is the minimum structure you can use? That facet size you can take it. That even circular also you can use it. So these are the concept about the concentrator and the tracking. And the tracking means, I already told you, three important components. One is concentrator, second one is receiver, third one is tracking. So tracking, we'll see that here minimum 2-axis tracking is required for the solar parabola dish. 2-axis means why? How to do that tracking means because sun is moving from east to west actually. So we have to track the system continuously, because our entire dish and the receiver will be a single unit actually. Now we can track the system only, whole weight is there. We have to track the system continuously. You can see that one is the parallel axis, parallel to the earth rotation, and other one is perpendicular to the earth rotation. You can see that parallel to the earth rotation, other one is perpendicular to the earth rotation. You can see that the first one, azimuth and elevation mount, that is the commonly used tracking system for the solar parabola dish. Even if you go everywhere, there is sometimes 1 or 2 cases only I have seen polar and declination and roll tilt, but most of the cases are azimuth and elevation mount will be used. You can see that azimuth elevation tracking is there, because sun is moving from east to west for that elevation tracking. And azimuthal tracking means seasons, whatever seasons I said, no, that is summer solstice, winter solstice, and March and September equinox. Accordingly, you have to turn the system, because every day east to west it will move, but how it is going the east to west, that is very important actually. That's why the seasons, if you understand that, and the declination, if you understand that, then it will be easy for you. For azimuth elevation mount tracking is commonly employed in that tracking system. And second one is polar and declination mount. And third one is roll and tilt. You can see that dish is placed there, and then roll and tilt, how to track the east to west, how to track the this tilt tracking, and similarly declination tracking, how to use that. And latitude is placed above the at the latitude angle of the place. Little bit, but this is one of the easiest thing we can install that actually azimuth and elevation when compared to the roll, tilt, and then polar declination mode. And receiver, second one is receiver. I said actually the receivers is the main component. It is a play a major role to convert the solar to thermal energy. That is even if you are using PV photovoltaic in the receiver, then solar to PV also will be there. But now receiver purpose is to convert the either solar to thermal energy or module. You have to place it. The receiver means sometimes you can place the PV module also nowadays. We are going to see in the later slide. If you use module, it will act as a module only. It's not a receiver. The receiver, main purpose of the receiver is to convert the solar to thermal energy. That is the thing. So two types of receivers are normally used in the constant solar power. One is flat receiver, other one is cavity type receiver. The flat receiver means it is not insulated actually. It is bigger size. Normally it is deployed in the solar cooker type, solar parabolic cooker. You might have heard actually. I have shown the picture also. There flat or surface receiver will be used. There more heat losses will be there. And the cavity type means it is for power generation type. To reduce the heat losses, such as receivers are nominated. Actually, such receivers are used actually. Cavity type receivers actually. Here heat losses will be minimized actually, because that's why solar to thermal conversion efficiency is very high actually. If you see 80% efficiency, I have shown in the solar parabolic dish. How that 80% efficiency means by means of cavity type only, because heat loss area is minimum, and then the area is also very small. Now we are coming to the thing. What are the errors involved in that? How to overcome all those things? We are going to see. Already I told you can see the two dishes. One dish I had drawn the parallel rays, and the dish I had shown the conical rays. Which one is correct? Conical rays is correct actually, because that is from the sun we are getting the conical rays only. It is not parallel rays we are not getting. That parallel rays, if you closely see, that is a conical only actually. So that conical rays is coming from the sun, and then after reflection from the concentrator, it will be diverged actually. Why it is diverging? Because of error. If the point is not perfect parabola, so this divergence will be taking place. So what will happen? Instead of getting a point, we will getting an area actually. So area means accordingly you have to design the receiver actually. Now what are the errors we will get in the fabrication? Means optical error, manufacturing error, facet alignment error, receiver alignment error, tracking error. So how to overcome all these things? That is the thing we are going to see. So optical error, that is glass. Already I told you, even if you use small facets actually, no sir, my dish, my parabola is perfect, but I want to use the mirror, means go for small facets actually. And manufacturing error, that you do in accurate CNC machines you can take that, but bigger size parabola means it is very difficult actually. So such error can be minimized by making the extra caution, that is designing the parabola shape. That is the thing. And facet alignment. Facet alignment means if you are aligning the mirror according to as per the contour of the parabola only you have to align. If you are using flat facets, say for example, obviously if facets will be flat actually. Suppose your subtract is parabola, but if you want to align the facet in a flat sector of huge, that is bigger length, then it will act as a slope only. That is, it's straight line only. It's not a curve path. So such things, facet alignment error will be there. And receiver alignment error means exactly you have to play the focal point. That is very important. So if you are misplacing somewhere, say for example 40 centimeter is the focal point. Let us imagine 40 centimeter is the focal length. You have to place your receiver exactly at 40 centimeter, or from the receiver midpoint should lies in the 40 centimeter. If you are placing above that 40 instead of 45, or if you are placing below that instead of 40 35, then error will come. That is receiver alignment error. And of course, third last one is tracking error. The tracking error means how you are using, what type of tracking system you are using, and how you are tracking the sun, whether it is exactly coincident with the sun's thing. All those things you have to see that. These are the errors, possible errors in the solar parabolic dish manufacturing. These are the ways to minimize that. And how to solve all these things means, one best thing is that is compromising the cost and the performance. What are the ways means, because I don't want to go for high cost, but I want to go for low cost, but the performance I will compromise. That is one thing. And second thing is Okay, let it be my dish is a low cost dish, by I can concentrate on the receiver side. Receiver side, I will use the receiver in a pakka manner so that it will capture all the radiations. That is another concept. And is let it be the low cost dish, I will use the secondary reflector. One more concept is there, secondary reflector, that will be deployed at the focal image point of the primary receiver, so that further deviation rays will not be going outside, it will be concentrating onto the receiver. That is another scope. Now, these are the dish we have produced during my PhD studies. Actually, this is made up of acrylic mirror. You can see that, and then based on the designing of the dish, we have gone for the receiver design. So we got the almost the flux distribution remains same actually. After that, and then error we measured actually 29.6 milliradian. Imagine what is the total error? It's 29.6. That is 1.7 dispersion angle, and the obtained focal image is 30 centimeter. These are the three types of. Already we published this paper also. We have considered the three receivers for the dish, and then we have done the analysis for the modified cavity receiver. These are the ways to address the problem actually. So we have taken low cost dish, okay, and then we have concentrated on the receiver. So receiver, we want to design it in a proper manner. So we want to estimate how much amount of total heat losses, how much amount of heat gain, what is the efficiency of the receiver. Like that, we predicted everything, and then we predicted our own design actually. We have assumed our own design, and then we proceeded, and then we checked that how the receiver will be. This is by using a ray tracing only. We have done flux distribution ray tracing. In that we found that whatever the proposed receiver, this is called as a modified cavity receiver, that will be as lowest heat loss. That is, we produce like heat loss is very small, very less actually in compared to that. We have done some CFD simulation also, how the air flow will take place during the different orientation of the receiver. Orientation means during at 0 degree is the sunrise, and 90 degree, 180 degree is the either you can say 0 to 90 degree is the 12 noon, and afternoon it is in the 90 side actually. That is in the 0 again it will come the sunset actually during that time. So that is, orientation is there actually, receiver orientation. We want to see what is the effect of air inside the receiver. That also we produce the ways to address the receiver issues. One of the receiver issues. Now, second one is we have introduced the secondary reflector. What is the purpose of secondary reflector? Means whatever the direct rays is coming from the solar parabola, that will be again converging to one particular point. After incident on the secondary reflector, it will again undergo multiple reflection and then it will enter into the receiver. So we have considered the three things: conical and compound parabolic collector, and then trumpet reflectors. These are the different shapes we have taken. These are the solution for the receiver problem actually. So what are the problems occur in that I'm providing the solution also. So these are the ways we can use. Now we have taken the trumpet. Now we can also take the conical shape. In the later studies, what we found, the conical shape also play major role. That is conical rays also will give the lowest convection. So you can see the trumpet shape and then conical reflector CPC, and then we have taken the temperature contours for the second reflector, and then we predicted the heat losses. So we have truncated the same height of the trumpet, and then we have developed the receiver, second reflector, and then we fabricated the dish. These are the modified cavity receiver we have done, and the reflectors, acrylic mirror we use. The dish we have developed, and then this is a low cost dish. Efficiency actually, efficiency, the receiver we concentrated actually. So one of the major problem is the receivers and the concentrators. So this is the one way to address the problem. These are the specifications involved in that. You can see that the constant ratio is 274 and the rim angle is 70 degree. You can see that the effective constant ratio, number of mirror faces 48. Still you can, if we have used the bigger facets actually, still you can minimize the size of the facets actually. So still you can reduce the image actually. That is the thing. These are about the problems related to the solar dish actually. One is the problem we are facing with the that is what type of reflectors. Nowadays the reflector coatings they are increasing actually. Now they are taking the subject and then high reflectivity material they are coating actually. That is also another way of solving the increasing the reflectivity also. And if your reflectivity is increasing, suppose if you have 0.85 and it will lead to 0.9 only the dish efficiency will be improved actually. Dish efficiency. but mainly the heart area is receivers. Receivers play a major role. Different shape of the receivers are coming actually. That is related to the conical shape, modified cavity receiver, all those things. So we can, next is the next concerning solar point is solar parabolic trough actually. Here the ideal case whatever we have seen there 46,000, here it 215 only actually. Yeah, that is ideal
Hello, hello. Hello. Can I call?
Yeah, now it's okay, no, sir? Okay, okay, I will give, sir. Yeah, yes. Okay, no, sir? Now it's okay, no? Okay, sir. Thank you, thank you. Thank you. So these are the problems involved in the line type concentrating solar power plant. How to address these things, all those things also you can take the receivers actually outer selecting receivers, receivers, such line focus type receivers be installed actually, and then you can see the heat aspects, how to minimize the losses, how to only that optimal only to use as insulation material. So these are the problems involved in that line focusing type. Uh, Next one is the linear funnel reflector system. That is linear funnel reflector system. Here the thing is optimized. Already I told you parabola, but only the mirror individual elongated mirrors are used. Each individual mirror can be tracked instead of tracking the whole system. They are tracking only the mirrors actually. That is the advantages here. And then each mirror is in the east side, and the west side can be tracked effectively. And the east side is in the west side means that the east side mirrors can be undergoing the tracking system. Like that, we can minimize that. Is it okay, sir, now? Yes, sir. Okay, sir. Okay, okay. Okay, sir. Yeah, thank you, sir. So these are the areas. Here we have to transfer the heat from the receiver to the down also, because we want to generate the steam, means the receiver is at the top actually. So we will circulate the heat transfer fluid. That heat transfer here they use sometimes in the central receiver they use the molten salt only. It is the molten salt, it will go and take the heat and then it is come in and stored in the hot salt malt storage also. You can see that. So the structure, how to efficiently capture the temperature, that capture the heat actually, retain the heat, all those things are very, very important. So phase change materials are used actually, and then construction of the concrete materials also play a major role, and how to transfer the other fluid, the heat from the molten salt to the other, say for other fluids, water, to convert into steam. So that is, after one steam is generated, that will be transferred to the Rankine cycle, like through our normal Rankine cycle, so that for it will fed to the turbine actually. So the steam generation part, how to retain the steam, all those things are playing major role here. So phase change materials will be playing a major role. How to retain the heat. Main thing is polishing, that is cleaning the surfaces actually over time. Nowadays automatic cleaning also there. Depends on the, suppose if any sand accumulation is there, automatically that sand will settle at the bottom. Like that, the surface coating also given in the reflectors actually. Such techniques also we can use it here. In the power tower actually, that is central receiver. These are the mainly problems involved in that. You can see it here. So here mainly concentrating, you can consider the receivers actually. Receivers molten salt tank actually, and how to retain the heat, phase change materials, and concrete materials, what type of concrete materials you can use. So these are the heat storage problems available in the central receiver. For us other type of point focus, line focus, mainly receiver is the main problem, and then how to make that structure is the another problem. These are the two problems are there. Receiver means we can compromise by mixing the selective coating and then evacuated receivers. Evacuated receiver means receiver tube is there and it is enclosed by another glass tube. So in between the surface, glass surface, and the in between the cylindrical surface and the glass, the space is completely evacuated, so that it minimize the losses, conduction, convection losses. Only radiation losses will be there, so that losses will be minimized, and then high efficiently we can transfer the heat to the working fluid. And then what type of receivers we are using, how much support we are giving, and whether a sagging problem is there or not. All those things we can concentrate, and then two-phase flow is there or not, two-phase flow problem is there or not, that also you have to study. These are the hot research areas in the concentrating solar power technologies, and then these are about to solar to thermal only. Suppose if you want to use solar module, solar PV module at the receiver, then the purpose of the receiver now is instead of transferring the fluid heat to the fluid actually, here we are converting the solar to electrical energy only. So such cases, how it will be, that what are the issues are that also we'll see that. So here active and passive cooling technology for concentrating solar power technology. So why active passive cooling, that we will see in the successive slides. The concentrating photovoltaic means, what do you mean concentrating photovoltaic means? You can see the panel, conventional available panel, say for example 100 watts is there. The same 100 watts can be produced in a small single solar cell, that is concentrating solar cell. Whether it will minimize the number of solar cells, but the only thing is it will produce the same power. Like that, that is why it's called a concentrating photovoltaic. Either the concentrating means can be done by using reflectors or lens. If you are using lens, means the Fresnel lens will be used properly. So it will be by means of refraction, it will focus onto the cells. If you are using lens, reflector means by means of reflecting, by means of reflection, it will, the rays will be reflected onto the receiver. In the receiver side only we are placing the module actually, PV module. Is the other technology. Other technology means CPV technology actually. So normally this is the typical IV characteristics, current and then open circuit voltage. If you see that, that is mean power point, that is maximum power point, and then maximum power point, that the current actually, and the voltage, maximum power point, the voltage, you can see that, and how to find the efficiency, that is PM by A, that is how much amount of area you have taken, and then how much amount of insolation. Insolation means incident solar radiation. That is how much amount of insolation is there. All those things based on that we can find the fill factor. Fill factor means how much that for if you purchase the solar cell, at the backside it has given manufacturer details have been given actually. How much, what is the fill factor, what is the IOC, what is the VOC, everything. So based on that we can predict the efficiency of solar cell. This is the typical conventional PV panel curve, IV curve actually. This is the thing. So what will happen if this curve is, you can see VOC and ISC, we can see that VOC and ISC, you can see VOC and ISC is there. So what will happen when you place this module at the, under the concentrating solar radiation, when high solar radiation take place means current will increase, but voltage will decrease actually. That is the main problem we are facing actually, normally in the so for that thermal management is required actually. We have to cool the solar cells. So you can see it here. Suppose it depends on the solar cell, how much amount of decrement is there, that you can see in the slide. You can see that as the temperature increases, VOC decreases and the current increases actually. That is the thing. So we have to effectively implement the cooling technology so that to maintain the operating temperature of the solar cells. That is very must. And then this is the major problem involved in that. Thing. You can see that if you use different types of solar silicon, that is crystalline solar cell, amorphous solar cell, you can see that the drop in the temperature is 0.25 to 0.5 degree, 0.25 to 0.5% per degree. Actually, you can see that the drop in the efficiency actually. So maximum 0.25 to 0.5. If you accumulate this per degree, so that the error, that is efficiency will be reduced actually. For that, module temperature should be operated at the operating temperature point. Now the different companies, Flatcon and Concentrix, different lot of companies are there actually. They are working on the CPV actually. Now the thing is, if you place that CPV module by purchasing the solar cell, concerning solar cell, and then by making the module, and then if you place it at the bottom of the receiver, then what will happen? Huge amount of heat flux is available at the focal point. Here the focal point is the module actually. So now if you place such a huge amount of heat, if you expose the solar cell on huge amount of heat, after some time it will, within a fraction it will melt actually, or it will distort. So what will happen? We have to effectively, we have to cool the solar cells, cool the modules, either solar cells or the modules. You can see the, here I have shown the single solar cell. You can see the efficiency, 33% efficiency, and the constant ratio is 1025. So 1025 means 1025 into 1000. That is one concentration ratio means that is 1 into, suppose if you are taking 1000 watt per meter square as 1 sun means constant 1025, and the efficiency is 33, but still improved also. A lot of cells are 36% is also there. And then what are the ways to address this issue means we can use extended fins, micro channels, phase change material, nanofluid, water jet, and two-phase flow problems. Two-phase flow, and that is phase forced convection. These are the ways to address the thermal energy, how to eliminate the thermal energy of the solar module. So if you are using single cell means no problem, we can use fins actually. If you are using hello, is it clear?
Yes, sir. It is clear.
Yes, sir. Yes, sir. Okay. These are the ways to address the cooling, that is thermal management of CPV cooling technology. If you are deploying that CPV module at the bottom of the receivers or at the focal point of the system, then you have to go for cooling. That is must actually. So these are the problems involved in that this thing. How to address this? You can use the fins, micro channels, phase change material, nanofluid, water jet. These are the ways. When we have to go for fins, when we have to go for active cooling. So if you use the fins means, if you are using very single solar cells, ratio is less than 150 or 100, then you can use fins actually. If your constant ratio is greater than 150, then definitely 100% you have to go for active cooling only. Otherwise, it will start actually. That is the thing. And these are the, you can see the what you mean by passive cooling. The solar cell is there, and then it is lens is, the fins are inside. You can see that for single solar cell, for linear solar cell, and this is solar cells. You can see that lens, and then fins are usually heat sink material. Sometimes they use the coupled passive as well as active. This is the concentric photovoltaic module. You can see the lens, and then fluid is there actually. Heat pipe is there. You can see that. In that fins also there, and then cooling. This active cooling. You can see the coolant is sent and to remove the heat actually. That is the active cooling. Some active and passive cooling also will be there. Already shown you. These are the active and passive cooling. Both fins as well as the heat pipe. You can send the coolant also. You want efficiently keep the operating temperature of the concentrating photovoltaic solar cells. And I have worked in that solar cell. That I will give the case study of that. I have worked in active solar panel initiative system. This project is one institution involved in that. One of the institution I worked with the Heritot University, UK. There they developed that. The main objective of the system is whatever the conventional PV panel you are seeing outside, they want to replace that. They want to replace that PV panel and they want to put the concentrating PV panel. That is the thing. The conventional PV panel means that is whatever the rays is coming, only that will be available. The concentrating, whatever I'm telling, concentrating photovoltaic, whatever the rays is coming, it is 10 times, 20 times it will be going to the cells, so on the solar cells. So that the same size of the system, same size as the conventional PV panel, similar to the CPV panel, it will produce more power. That is the thing. It is undergoing the internal dynamic tracking. That is inside dynamic tracking will be there. From the outside you can't see the tracking. Only at the inside only it is there. You can see the things. It is basically parallactic tracking. It is the principle of parallactic tracking, up, right and left and up and down. Because you cannot see from the outside, you cannot see whether it's tracking or not. If you clearly watch the inside the PV system, inside means the system is covered with glass actually. If you see, then only you can see that some tracking system is there. So it's called internal dynamic tracking actually. So here this type of system will be there. It is a elongated solar cells are used actually. Fins have been used. This is the concentration. The main purpose of this project replacing the conventional PV panel to concentrating photovoltaic panel actually. That is so here the lens they use the funnel lens, and then the solar cells they use elongated solar cells. That is maximum to 10, 20, 50, 100 like that. 3 step of concentration we have fabricated and then we have tested also. So you can see that this is for 10x. And this is the cell length, all those things are there. You can see that this, like this system will be there. The same type of system will be placed at the conventional, replace the conventional PV panel actually. So we have studied what is the temperature of the solar cells, and we predicted what type of if we fins 4 number of fins, what will happen, 3 number of fins, like that. We predicted if a numerical simulation also we have done the temperature, what is the glass temperature, all those things we implemented here. These are the problems we faced actually. And you can see that clearly as the temperature increases, how much the deviation is there. You can see that 75° means the enormous drop in the open circuit voltage, but small rise in the current actually. You can see that. Now we have studied the system actually, and we have argued the solution also for that. Now apart from that, just solar power plants. You would like to show whatever this is the that is solar parabolic trough actually. You can see that it is 354 megawatt. It's in California. And this is the tower, central tower. You can see that heliostats are there and central chimney is there. That is the thing. And then these are the heliostats, 6 megawatt. This mainly in the large area only this power plant will be used actually. Only parabolic trough in the commercial side it has come, and the central receiver it is only for huge scale. In solar parabolic dish it is also commercial, it's about to come, but still in the R&D only. Modular type is come actually, modular type, small cap, but only thing is the small capacity is even if you want to produce 1 kilowatt you can produce. You want to produce 10 kilowatt, you can produce in the solar dish. Whereas in the other system, it is not there. Only for minimum minimum capacity is required actually. Solar parabolic trough, central receiver, and then this solar parabolic linear filter. So this is the CPV based. You can see that CPV based solar cell. That is the station actually. You can see that this is a 500x higher concentrate ratio they used. They used multi-junction solar cell high efficiency. That is the thing. You can see it. And these are about the problems, and then what are the problems we are facing, and then how to address the problem also I explained actually regarding this concentrating solar power technology. And the work we are doing at NIT Puducherry regarding the CSP also I will share that. So we have developed the system, and then we have checked it with the nano fluid, active cooling material, and then we used the solar cells actually. So here of course we have used 2 solar cells actually. sorry, it's one solar cell we have used actually, spectral solar cell, but we have sent the nano fluid actually. We want to check how effectively we can cool the solar cells, all those things. But anyway, concentration is more. This is the nano fluid preparation, and we have implemented the spectro solar cell from the US actually. We purchased it and then we implemented at the focal point, and then we tested that. This will produce around 30 watt actually. You can see that this is the cost we are in, and apart from that we are working in the low temperature. We are working in the LTD system, that is low temperature thermal desalination. At low, we are taking the seawater, and at a low temperature we want to flash, and then we want to condense it actually, so that we will get the pure water, drinking water. See that. For that we are using the solar parable dish, and then we are tried with our solar parable dish as well as the CPV, concentric CPV, and then we want to produce that DC and then desalination. So 3D we want to produce actually, DC power and the desalination, and the dryer also we will include actually 3D. So that we are going to see in the next slide. So in that intention only I'm showing all these things. This is the, for that designing the parabola dish you can do in the MATLAB simulation also. You can get the reflectors also. This is the reflector, what is the slope error, all those things we can predict actually. What is slope error? And if the MATLAB, if you place the reflectors, what will happen? How much reflectors error will be there? So this is the plane phase mirror. I already told you. This is the phase mirror we have taken, and then we have installed. This is a 2 meters per dish. Further, we have done the ray tracing. Ray tracing means how much amount of radiation is there actually coming from the sun, and how much it is going to the receiver. Also, ray tracing we have done in the MATLAB. And then the receiver, we have taken the different shape of the receiver because we have taken the satellite dish only. We have taken. We are not taking this whatever the satellite dish. Actually, this accurate shape is there. In that, we are placing the facets actually. So for that, how much amount of ray tracing we have developed actually. Ray tracing we have done, and then we have implemented the receivers, different shape of the receivers, dome shape, conical shape, like we have designed implemented the receivers, and then we have done the how much amount of flex is available. So different planes is available, which one will be better. Like that we developed our, we are doing the research, and that we find that conical shape will be the better when compared to the dome shape actually. Conical shape will be very less heat losses, and then the flex is also very high actually in that. So that's after that we put the conical shape of the receiver, like the circular tube we have made, and then tracking system we developed actually, dual axis tracking system. We have developed that, and then so that it will track the sun actually. So for that, the 2 meters per dish we have developed everything. So this is the tracking system we implemented here, and then module, whatever the CPV module we developed here through the spectral lab, that we are taking the module actually, and then we implemented at the focal point actually. So now we have tested that, improved the focal point, but still that problem we are facing actually, effectively cooling system not. But thing is, you can see here we have implemented the solar parabol dish with the CPV and conical receiver and the DC power, and then we want to develop the because why we circulate the water means we want to cool the solar cells actually. That water we have, sea water we are taking, and then we want to remove the heat by sea water. That's the heated sea water will go to the flash chamber, and that flash chamber will at a low temperature it will be evaporated. Low temperature will evaporate, then the evaporation will be condensed actually in the condenser, and then we will get the pure water actually. That is the thing. These are the 3 ideas actually. That is conical receiver, and then with the tracking system we want to use. That is the thing. So this is the thing we have used actually. And apart from that, this concentrating solar power, we are working in the desalination, but we are planning to use the concentration on the PCM and the desalination. This is the PCM material we used. Material side also we are using, that is phase change material. We are using the paraffin wax, and then we have mixed with nano fluids, that is nano particles, and then we are trying to study actually. This is the thing. And then dryer. Already told you 3D. 3D means DC power, desalination, dryer. So in that aspect, we are working actually. This is the solar dryer actually. We are drying the vegetables, and then that is vegetables, and then fish. Because in Karaikal, we are at the Karaikal actually, NIT Puducherry, located at Karaikal near to seashore. So we are taking the fish, and then we are drying, and then we are developing the drying kinetics model also. Okay, like that also we are doing. And then concentrating power means we have got the project actually in the DST. So we have developed the concentrating solar parabol dish and then we have constructed that different types of, you can see that we have developed the receivers for that flat receiver we have developed, and then we are doing the analysis also. These are the project work, the DST project work we got, and it's completed actually. This is the project about the information. This is the thing. And the next project is, apart from that solar, we are working on the fuel cell also. Fuel also in the, along with Dr. Karthikeyan from PH Tech, and we are working in the DST UKRI project. The project is completed actually now, along with the University of Lavabara. And now recently we got a project with Brazil, that is in the BRICS project, along with the NIT Trichy actually. So we are working in the biomass also. The life cycle analysis of the that is biomass, whatever we have taken actually, locally available biomass, and then we want to study in that. So this is the another project. So if you want anything related to the information about the what type of works we have, what type of concerning solar power system we have taken, on what receiver design, so you can refer our papers here. And if you have any doubt, also you can send email also. If in future, if well, because I have been working in the solar parabolic dish almost 13 years actually. So whatever the problem we are facing, that also I will share with you if you want actually doing the things. So if you are facing any problem, you can discuss with me through emails actually. Now there are a lot of ways to doing the things. Now whatever I shown that is very small, still you can also explore the things to find the things, better things to do the things. So that is the thing. There are always better ways of doing the things. Our challenge will remain to find them out. And if any questions, feel free, and then you ask the questions. I will happy to clarify that.
Good afternoon, sir. Hello, good afternoon, sir.
Hello, sir. Yes, sir.
Sir, I attended your lecture and it's a very informative session, sir. Quite information we are getting. Sir, actually,
Yes, sir,
I want to pursue PhD in this solar field. So recently, I enrolled in this program. So I want to know that, sir, what is the future scope? Like, if I want to go for the parabolic trough collector, so let me give the guidance about this, sir.
Actually, instead of taking parabolic trough, because it is commercialized now actually, lot of technologies have come actually. Only you could consider on the receiver side actually. Parabolic trough means you can consider the system, you can consider the receivers. My suggestion is better you can consider on the parabolic dish side, still in the research stage only. So you can design the new receivers, you can optimize the shape, lot of works you can do.
Okay, sir.
The parabolic dish side.
Okay.
Yeah, especially receiver side, you have to concentrate actually. Even you can take any type of concerning solar power system, the receivers you can take it. It will be very good actually.
Okay, sir. Okay.
Lot of scope is there, research scope is there.
Sir, one more question is that, we can focus on a concentrating Scheffler parabolic trough collector,
Scheffler type. You can, parabolic trough is a Scheffler type. Scheffler type, that is elliptical shape, you mean to say, or parabola shape?
Elliptical shape, sir.
Elliptical shape, that anyhow they proved it is parabola is the best actually, sir. Elliptical we can use that actually, but how efficiently you can use that receiver design, you can say that you can consider the receiver side.
Receiver side. Okay.
Yes. Because we have to minimize the heat losses. Major thing is heat losses will be more actually. So you have to do the research how to minimize the heat losses, what shape of the receiver, what size you can take, and that you can optimize that.
Okay, thank you, sir.
Yeah, thank you.
Sir, good afternoon. Myself Depas from Centurion University. Sir, actually for reflecting material, what should be the suitable material we'll take so that the reflectivity will be more and
mylar one material is there. Mylar, it is a aluminized anodized coating. Mylar sheet is there that you can use it, or otherwise nowadays thin film coated things are also there actually, high reflectivity material that also can be used. In the low cost means you can think about the acrylic mirrors or any polycarbonate, and then you can apply for your coating also, or any glass surface you can take in, and then you can go for coating also. Suppose if you want to increase the reflectivity, you can go for new coating, and then the only thing is you cannot bend the mirrors actually, but bending it will take cost will increase actually. Depends on the shape of the parabola, you have to bend the mirror, then only it will occur the contour of the parabola. Otherwise you have to use the flat facets only on those things.
Okay, sir, thank you.
Okay, thank you.
Sir, I request you to kindly provide the contact information. So for further research study, if I want to get some guidance from your side. So
yeah, my email ID is there, sir. You can take the thing. My email ID is there. You can contact
okay,
me,
sir.
sir. Here it is there actually. You can take the email ID. And later
Yeah, yeah.
stage, if you are working in the solar power dish or constantly, feel free and ask me. I will support you, sir. I will help you.
Sure, sir. Sure. Thank you very much.
Yeah, thank you.
Participants, any other question? Okay, sir. I think there is no other question.
Okay, sir.
So thank you very much for the wonderful session, sir. For past 1.5
Yes, sir. Thank
hours,
you.
we have learned so many things from your presentation. I know that now classes were started and
Thank you
you
so
people
much.
are very busy in NIT. That too, for a head of the department, how much works will be there, we can imagine. But instead
Yes,
of
sir.
that busy schedule, you gave one slot to us and you had taken a nice session. So everybody enjoyed and everybody
Yes, sir.
got
Thank you.
some
Thank you,
valuable
so much, sir.
information from your session. So on behalf of the Department of
Thank you, sir.
Mechanical Engineering, Jyoti Engineering College and AACT ATAL Academy, my heartfelt gratitude to you, sir, for this
Yes,
nice
sir.
session. Thank you, sir. We hope that in future
Yes, thank you.
also
Thank you so much.
we
Thank you,
expect
sir.
your support for organizing the events and also for some collaborative research works if possible.
Yes, sir. Definitely, sir. Feel free to approach me. Anything. In between, I could not because I did not know that the internet connectivity.
Yeah, sir. Yeah,
So,
that I understood, sir. Because
because I am the
in
PPT.
full PPT mode, we can't see the things. That's why I called you immediately.
Yes, sir. Okay, sir. Thank you, sir.
Okay.
Thank you.